Yeah, so there are lecture notes that you can find at this address, which cover the lectures and a little bit more. We are going to avoid that this time. Okay, so if you want to have the content of the previous lecture, you can find it there, and you can, of course, ask me any question on these lectures. So last week, we introduced what we called spin models. We introduced what we called lattice, geometric representation of these lattice models. And we did a crash course, nothing more than that, on Bernoulli percolation, which would be the archetypical example of a percolation model. And as I said, these geometric representations are usually dependent percolation models. So to see the simplest case, this independent case, could give you ideas of what you want to prove on these models and how you can prove them. And you will see that we are going to go back to this type of things later in the class. So today's class is going to be a little bit a transition between this previous class, which was the introduction and where we saw different results and what we would like to prove and so on, and really the proof of these facts, which will come mostly next week, next class, which is in 2 weeks, and in the last class. So here I'm going to introduce really a geometric representation. I'm going to spend a little bit of time introducing it because the definition is a little bit less trivial. And I will mention what are the equivalents of the result that we had for Bernoulli percolation in this context. So not many proof today. But still, I was not completely finished with Bernoulli percolation, so I just want to finish a little bit. So it will take me maybe 20 minutes to give you a last theorem, 2 last theorems on Bernoulli percolation. OK, so let's start. First thing, for those that were there last week, so I finished the proof of the exponential decay for Bernoulli percolation. I just want to do 2 remarks. So this will make absolutely no sense to people that were not there last week. But it's really just 2 remarks. So the first one is, as I said, phi p of the singleton 0 is p times 2d. OK? But remember that we said that PC is the infimum, or the supremum of the P for which you can find one set such that phi p of this set is strictly smaller than 1. So what does it imply? It implies automatically that PC of d is larger than 1 over 2d. So the critical value of Bernoulli percolation on ZD is larger than 1 over 2d. And this is the bound that you would get by doing the classical Peirce argument. OK? But here it falls down completely trivially from the proof. And so in particular, it tells you that PC is bigger than 0. OK? The second comment is a little bit more interesting. So at PC, we have that phi p of s is always larger or equal to 1. OK? That's a property. So in particular, phi p of lambda n is larger or equal to 1 for every n. So what does it mean? That means that p times the sum for x in the boundary of the box of size n of the probability that 0 is connected to x in lambda n, this is larger or equal to 1 for every n at PC. Sorry, PC and PC. OK? But now sum on n, and notice that this implies, so by summing on n, what do you get? Well, you get that the sum for x in ZD of the probability at PC that 0 is connected to x, well, this has to be larger or equal to the sum of these things, which is larger than 1 over PC. So this thing is infinite at PC, right? So this is what? This is the average size of the cluster at 0. So the expected size of the cluster at 0 at PC is always infinite. In particular, it implies that you cannot have exponential decay at PC, right? So that was the 2 comments I wanted to do on last week proof, and now I start fresh. So this is very important because you will see that for some dependent percolation models, this doesn't occur at all. I mean, there is exponential decay at PC. Okay? So now that we have this, we can try simply to compute PC on Z2. So computation of PC on Z2. And this is a very, very famous theorem by Kesten, which goes back to the 80s, that PC on Z2 is equal to 1/2. So the critical value of percolation on Z2 is 1/2. And it is a tough theorem. It's really not very easy to understand the proof. It's a very natural proof, but it's a little bit difficult. So what I propose is to give you a simple proof using this the theorem of exponential decay that I showed last week. So I guess with the proof of exponential decay of last week, it's perhaps the shortest proof you can provide. So let's define Z2 star, the dual of the square lattice, to be just the shifted lattice by 1/2, 1/2. So what is it? You just take the square lattice and you put vertices in the middle of faces and edges between nearest neighbors. So you get a translate of the square lattice. Now for any configuration, so if you take an edge E on the square lattice, you have exactly one edge of the dual lattice which is crossing it in its middle. Okay, there is this edge here, which is crossing it in its middle, and I will call it E star. Okay, so every edge of the primal lattice is naturally associated to an edge of the dual lattice. Now, if I look at a configuration omega, so a percolation configuration, it's a percolation on edges. I can associate to this percolation a percolation omega star, which is going to be defined on 0, 1 to the edges of the dual lattice this time. By doing what? I'm just going to say omega star of E star, so the state of the edge E star, is open if the edge E is closed and closed if the edge E is open. So this thing is going to be equal to 1 minus omega of E. Okay, so I have defined like that a percolation configuration, the dual configuration on the dual lattice. Now, just a trivial remark. If omega is sampled according to a percolation of parameter P, then omega star, well, it has to be sampled according to a percolation of parameter P star, where P star is just going to be 1 minus P, right? I mean, every edge is open with probability, well, the probability is that the edge, the corresponding edge of the primal lattice is closed, so with probability 1 minus P, and it's independent of the others. Very well. So now you see that 1/2 plays a special role here. It's the only point for which P star is equal to P. Okay? And so the theorem, due to Kesten, says, well, PC is equal to 1/2 on Z2. So indeed, this self-dual point, somehow, is the critical point. And I want to prove that. So note that at least, well, maybe let's not give, I'm not going to give you the intuition that, because a physicist will look at that and say, of course. And now we pass to the next step. I'm not going to tell you why he thinks, of course, because I'm going to tell you exactly these words and pass to the next step in 10 minutes when I will do it for dependent percolation models. Okay, but here I can provide the proof, so I'm going to do it. Okay. So first, let's assume that PC is strictly bigger than 1/2. This is going to be the easy case. So in this context, we know that at 1/2, we are in subcritical. Okay? We are strictly below PC. So by the theorem of last week, we know that there is exponential decay, right? So in particular, if I look at the event, so let's say 0 is here. Let's take the site N0. Let's look at the event that there exists a path of open edges passing through N0 and surrounding the origin, something like that. Okay, let's define this to be the event En. Well, if N0 is on a circuit which is surrounding the origin, at least N0 is connected to distance n. So since I am in subcritical, the probability of the event En is going to decay exponentially fast. This is the theorem of last week. So it's a non-trivial theorem. Okay? That's something which is not completely straightforward to get. But then, by Borel-Cantelli, since the sum of these things is finite, we can deduce that there is only finitely many n for which there is a circuit like that. So there are finitely many circuits surrounding the origin. So we deduce almost surely there are finitely many n such that En occurs. But you can see that if there are finitely many n such that En occurs, then what is happening? Well, in the dual configuration, there must be an infinite cluster. You can try to see why, but then this implies, as a consequence, that omega star contains an infinite cluster, almost surely. And this starts to be contradictory. I mean, it's even it's more than starts. It is completely contradictory because the dual configuration is a percolation of parameter 1/2. Okay? But P omega star is a percolation of parameter 1/2. Therefore, sorry? No, here I'm really working at 1/2. Yes, at 1/2. And so I need to be really just below PC, because at PC I don't know exponential decay. So this would work for any P between 1/2 and PC. But so I have that. Therefore, the probability at 1/2 of existence of infinite cluster is 0. So I have a contradiction. Okay? So once you have exponential decay, it's in fact easy to prevent this, I mean, to prove this inequality. So you should think in the following way. So if PC is larger than 1/2, there is no infinite cluster at 1/2, but there should not be also an infinite cluster in the dual. But when you have exponential decay, you cannot have absence of infinite cluster in the primal and dual model. This is not possible. But a priori, you need to rule out that. Now let's try to do the other inequality. No, let's let's prove PC larger or equal to 1/2. And this is an absolutely beautiful argument due to Zhang, who was a student of Kesten. And it's not in the, this is also an argument which is posterior to the first proof. So the idea is, I mean, it basically just comes from one drawing. So let's assume that we have that the probability at 1/2 that 0 is connected to infinity is strictly positive. Or, I mean, that there is infinite cluster, sorry, is 1. Okay? Then what can I do? Well, for any epsilon, so we are going to fix an epsilon. I'm not telling you exactly which epsilon, but an epsilon, a tiny, tiny, tiny epsilon. Think of 1/1,000,000,000. Then I can choose a box large enough that the probability that this box is connected to infinity is going to be larger or equal to 1 minus epsilon. Okay, because just when n tends to infinity, it tends to 1. So choose n such that the probability at 1/2 that lambda n is connected to infinity is larger or equal to 1 minus epsilon. So I have this big box. And I know that it's connected to infinity with very good probability. So this event, that this box is connected to infinity with very good probability, I mean, it's the union of 4 events. Sorry, I don't know how to count. The event that the top is connected to infinity, the event that this is connected to infinity, this or this. There are 4 sides. And the 4 events, they have the same probability, right? Now notice, so let's imagine, I'm going to do it with 2 events, but it works with 4. Imagine that I have 2 events, A and B, and that they are increasing, okay? So for those who were not there last week, an increasing event is an event which is stable when you add open edges, okay? And for this event, we know the following inequality, that the probability of the intersection of the 2 events is larger or equal to the product of the probabilities. It's called the FKG inequality. So let's assume for a moment that the 2 events have the same probability. And I know that the probability of the union of the 2 events is very close to 1. If the 2 events are a priori whatever event, the fact that the union of the event has probability close to 1 just enables us to say that, well, then the events, or at least one of the events, has a probability close to 1/2. Okay? And if they have both the same probability, basically, at least the 2 of them have to have a probability close to 1/2. But if they are increasing, you can do a little bit better, because this is what? This is 1 minus the probability of the intersection of the complements. Now, the complements are decreasing events, and you can easily see that if you have this for increasing events, you have it also for decreasing events. So this is going to be smaller or equal to 1 minus the probability of the complements. There is absolutely no chance I'm not going to screw up the inequalities, but we are going to see that later. Now, this is 1 minus the probability. 1 minus the probability, if I assume that the 2 have the same probabilities, is going to be 1 minus the probability of A squared. And when I put everything in the right order, I get that the probability of A has to be larger than 1 minus, well, the square root of 1 minus the probability of A union B. Something like that. So I get something better than before, because if this thing is close to 1, then this thing is close to 1. Right? So this is called the square root trick. And this is really something to remember as soon as we have an FKG type inequality. Of course, I did it with 2 because it was simpler in terms of notations, but you can do it with 4. There is no trouble. So what you're going to get is that since the probability of the union of the 4 events is 1 minus epsilon, at least, then the probability of each of the events is, well, it's larger than, so let's say that the top is connected to infinity, is larger than 1 minus epsilon to the 1/4. This is what you're going to get by using the square root trick. It's a 1/4 because you have 4 events. OK, so the probability of this, now let's look at the probability of this. So top and bottom connected to infinity. Well, this is larger or equal to 1 minus 2 epsilon to the 1/4, right? But look, I mean, it's not at p, it's at 1/2. In the dual model, I also have this property. The dual model is the same as the primal model. So the probability that this point is connected to infinity in the dual model, and this one connected to infinity in the dual model, well, this is also probability 1 minus 2 epsilon to the 1/4. So when I take the intersection of the two, I get that with this probability, I have this configuration. I'm cheating a little bit because the dual here, you know, it's shifted by 1/2, but this is really tiny, tiny things to change. There is nothing deep there. Does somebody see what starts to be contradictory here? So remember that we proved that the infinite cluster, when it exists, is unique. The probability of having 2 infinite clusters is just 0, right? That was this Burton-King argument. So when I'm there, I notice first that, I mean, this, what is inside, doesn't matter for the probability that, I mean, here, maybe I should have been a little bit more precise. I want this to be connected to infinity from the exterior. I'm not using what is in the box, OK? So then this event, this, and this, I mean, all this is completely independent of the state of edges inside the box. So now, if I pay a p, I mean, rather 1/2 to the number of edges in my box, I can just close all the edges inside the box. Close all these edges. What do I end up with? I end up with 2 infinite clusters. This cluster and this one cannot be connected anymore. OK? So I just proved that with positive probability, I mean, it's a terrible bound. This is, I mean, really tiny, tiny. But with positive probability, I have 2 infinite clusters, and this is contradicting the Burton-King theorem. OK? So basically, the fact that you cannot have an infinite cluster at PC is just at 1/2 is just a consequence of the uniqueness of the infinite cluster. That's the important step. So this bound is much simpler to get in general than the other one. OK. So that was, and you notice one nice thing, which is that as a very simple consequence of, direct consequence of all of this, I have also the following corollary, which is the probability at PC of 2 of 0 connected to infinity is 0. So the phase transition on Z2 is continuous. At the critical point, I don't have an infinite cluster. So let me just mention the following conjecture, which is that for every d larger or equal to 2, when I look at percolation on ZD and I look at PC of D, I always have this property. I never find an infinite cluster at PC. And this is a conjecture because, in fact, so it's known for D equal 2. It's known for D larger or equal to 15. So it was first proved to be true for D larger or equal to 19 by Hara and Slade. using what we call the less expansion techniques. So this less expansion is a way of comparing basically the behavior of the model to the behavior of the model in mean field. And in fact, this comparison should hold up to d equals 6. Problem is that technically it's difficult. I mean, you have convergent series and things like that, and you manage to prove they are convergent only for d larger or equal to 19. And that's the reason why it's only for large dimension. It was improved, I think, 3 years ago to 15, but I mean, there is still a long way up to 6, but at least conceptually, we understand why 6 is a barrier. These techniques will never prove you anything below 6. So dimensions 3, 4, and 5 are basically the big unknown. And proving that what we call, I mean, critical percolation dies out in dimension 3 is probably one of the biggest open problem in this field. So if you want to have your PhD or maybe a little bit more, then you can try to prove that. OK. So let me focus, I mean, carry on focusing on the planar case, because in fact, many of the theorems I will prove later on are restricted to the planar case. What can you say at the critical point? Well, there is a theory, which is a very important theory, which is called the Rousseau-Seymour-Welch theory. And I want to tell you a little bit about this in the context of Bernoulli percolation, because it's going to come back for dependent model, and there I will really be completely unable to give you the proofs because they are way too long. So at least here I can tell you a little bit about the nice proof that was presented, I think, like 8 years ago, and which is pretty quick. OK, so what is the theory of the Rousseau-Seymour-Welch theory? It's basically the study of the probability of the following type of events. Imagine you have a topological rectangle with 4 points on the boundary. The percolation, I mean, the Rousseau-Seymour-Welch theory is interested in the probability that there is a path of open edges going from this part to this part. And what we want to study is, we want to study this by fixing the shape of your topological rectangle and looking at smaller and smaller lattice. So the mesh size of the lattice tends to 0, and you look at this type of probability. So there are predictions at criticality for the limit of this kind of quantities, but we are not going to discuss this today. Actually, we are not going to discuss it in this class. There is a very natural and a very beautiful conformal invariance theory behind that, which is not known for the square lattice. That's why we will not discuss it. But so there are limits, natural limits for this type of probability. What I want is just to prove that these things do not tend to 0 or to 1, that they are non-degenerate. From a physical point of view, it will, I mean, boils down, I mean, it will be equivalent to saying that there are no correlation length at criticality. There is some kind of invariance under scaling. So rather than taking any type of weird shape, I'm going to focus, because that's what we will use. I'm going to focus on a special type of shape. So I'm going to say the following theorem. For every rho larger than 0, there exists a constant C, which depends on rho only, such that for every n, we have the following. The probability at 1/2 of having a crossing in the box of size n times rho n this probability is smaller or equal to 1 minus c and is larger or equal to c. That's going to be my theorem. So it doesn't tend to 0, it doesn't tend to 1. Okay? Uniformly in the size of the box, it just depends somehow. This bound, of course, depends on the value of rho. So before diving into the proof, maybe I should mention a few trivial comments. For instance, look at this probability when I look at a square, n times n. Okay? When I look at a square n times n, what is the complement event of this one? Of the existence of a path from bottom to top in the box of size n? Well, it is the existence of a dual path from left to right in the box of size n. It's a path that is blocking the path from bottom to top. So if I look at this thing, I get one. Okay? So that means because this is exactly the same event as this one, it means that the probability for a square is 1/2, basically. So I'm cheating a little bit once again because the dual of this n by n square is not exactly a n by n square. It's a n plus 1 by n minus 1 rectangle. There are many ways of just showing that it's basically the same. Okay, so I don't want to add details. And if you want a self-contained proof, you can in fact just use that it's larger or equal to 1/2. That's the only inequality we would use. I'm not cheating you there. So my point being, n by n, it's trivial, basically. It is 1/2, no problem with that. Now, on the other hand, imagine I tell you, OK, the probability at 1/2 of n by 3n over 2, I could have taken something else, but that's what we are going to prove. So probability of this thing is not tending to 0. Then you can prove that basically for every row, it doesn't tend to 0. Okay? First, for any row smaller than 3/2, it's trivial. And for any row larger than 3/2, what you can do is, so imagine you have a very long rectangle like that. Well, you can take a n by 3/2 of n rectangle and say, OK, I have a path like that. You can take a shifted by n over 2 rectangle, so which is going to go up to there, and say this is crossed as well, and so on and so on. The problem is that you don't know that these paths, they glue together, right? But the thing is that here you have an n by n rectangle. So you can just say, OK, this rectangle is crossed vertically. And now you are certain that this path and this path are connected together. So when you do that, the probability of the intersection of these things, since I'm only looking at increasing events, is going to be larger or equal to the product of the probability. So it's going to be c to the number of rectangles I need to use. So if I want to go to distance rho n, since I'm gaining 1/2 every time, I'm going to do it 2 rho times. And I also need to use this guy. So it's going to be 4 rho. So c to the 4 rho. OK? Let's take rho integer. So in this context, you always have a lower bound. I mean, you can deduce a lower bound easily. But notice that if you would have it only for 1 here, you cannot gain this n over 2 every single time. So in this context, you are completely stuck. So basically, the only difficulty is, can you get, I mean, you can try to do drawing. It's a pretty funny things to do. If we would have time, we would do it together. But basically, if you have only n by n, it's very difficult to see how you are going to manage to glue things together. So the difficulty is to get from nn to 3/2 of n, or to anything larger than 1. I should mention one thing, which is that's what we are taught at school, basically. I mean, at school at the university. That the difficulty is getting from nn to 3/2 of nn, because that's the difficulty for percolation. I would say that from a point of view, from a physics point of view, for really what matters, the real difficulty is lying rather in this inequality. Because for other models, this is not going to be true. You are not going to have things like that. And that's getting just one lower bound for one aspect ratio, which is really the important thing. Then there is a lot of work to get to larger distances, but I would say that the physics behind it, I mean, is rather saying that this is a difficulty. But for percolation, it's trivial, so this is the difficulty. OK, how do you get the lower bound? I mean, the upper bound, sorry, so this gives you the lower bound. The upper bound is simply, I mean, if you want, I mean, the probability of having a path like that is definitely 1 minus the probability of having a path like that, and then you use the Rousseau-Seymour wedge in the other direction, and you get the upper bound. OK, all of this to say that basically we only need to prove the following proposition, and the proposition is going to be the probability at 1/2 of crossing. So I'm going to put minus n. Here is going to be minus n, and here 2n. This is just a choice for, I mean, in the proof it will be nicer. OK, that will not fall lower. The probability of this is larger than 1/128. I mean, this bound could, of course, be improved, but we just want a lower bound. OK, so we are going to prove that. And you see it gives you an aspect ratio 3/2, so it's sufficient. OK, so the proof, I mean, there are many, many proofs of this. The first proofs were basically due to Rousseau, Seymour, and Wedge. So Rousseau on one side, Seymour and Wedge on the other one. It's contemporary, I mean, really at the same time. There were many proofs since then, and I'm going to give you a proof by Bolobash and Riordan, which is, once again, for those that were not here last week, I'm not writing all the names because they are all on the notes. So that's just to try to gain a bit of time. But they have, I think, the shortest arguments, really the cutest one. And once again, it's going to almost lie in one picture. So define AN to be the following event. So I have my n by, I mean, my minus n, minus n, 2n box. Let's look at the event that there is a path, there is a horizontal crossing of this box. So this is 0n squared, OK, which is connected, whatever, I don't know how, to the bottom of the box. Let's just look at this event, right? Is it clear for everybody, this event? So I want to prove that this event doesn't have a too small probability. And for that, I'm going to cut this event into several sub-events. So if AN occur, then I need to have a crossing of the box. OK? But now if I have a crossing of a box, I have a highest crossing. OK? So let's just, for a moment, choose a gamma crossing 0n squared. So I have a box like that. I have this box 0n squared. And let's choose a deterministic path crossing like that. What I can do is, so let's, oh, this is gamma. I can define the reflection of gamma with respect to this line. So I'm going to get, I'm extremely bad at this. OK, something like that. This is a reflection sigma of gamma of the path gamma. And all of this defines a set. Maybe this I want here, I should say, no, it's OK, sorry. I get a set below gamma and sigma of gamma, which I will call S of gamma. S of gamma. Okay. What is the probability in S of gamma that the bottom, this part, is connected to this part? Well, first, what is the probability that this is connected just to gamma union sigma of gamma? Well, it's definitely larger than the probability that this is connected to this, right? If I draw this. But I am in a box, in a square box. So the probability that this is connected to this is 1/2. So the probability that this is connected to this is larger or equal to 1/2. But now you have this, the probability that this is connected to this part is the same as the probability that this is connected to this part just by symmetry. So the probability that this is connected to this is larger than 1/4. Okay? So now how do I finish that? How do I finish? Well, I'm going to say the probability at 1/2 of the event AN, well, it's the probability of crossing the box of size n by n times the probability at 1/2 of AN condition on this. So far, so good. I didn't do anything smart there. So this is 1/2, we said. And now this, I'm going to decompose it with respect to every possible crossing of the box. I'm going to decompose it by saying I'm conditioning this time on the fact that capital gamma is equal to gamma, where this is the highest crossing of 0n squared. Okay, so this is a random variable. I'm conditioning it to be equal to gamma, and then I have a probability of 1/2 of gamma equal gamma, knowing that it's cross. Okay? So I decompose, I know there is a crossing, I decompose it by saying I decompose it with respect to the highest possible crossing. So this is a partition of the event, right? But observe that the highest possible crossing, I mean the fact that gamma is equal to that capital gamma is equal to small gamma, this depends only on edges that are on the path or above the path. I mean just measurable with respect to these edges. So anything below this path is absolutely undiscovered. I have no information on it. So that means in particular that the condition on capital gamma equal small gamma, the percolation in S of gamma is, just percolation, standard Bernoulli percolation. So the probability of AN knowing this is just larger or equal to 1/4. So this is going to be larger than 1/8, and I have the sum of a gamma of this thing that remains. But as I said earlier, decomposing with respect to the highest most crossing is just partitioning the event, so the sum of this thing is just 1. Okay? So I get 1/8. So the probability of AN is larger or equal to 1/8. So why is it so good? Well, because we are basically finished. Now we are going to be able to glue things together. So what is the probability now of the following? So I want the probability of AN. I'm going to also look at AN tilde, which is exactly the reflection with respect to this line. So probability that there is, so let's make a good drawing, a path like that connected to the top. This is the same, it's 1/8 again. You see that a priori these two paths, they do not connect. So I still don't have a path from bottom to top. But now you see what I'm going to say is that I can also assume that there is a crossing from bottom to top in this small rectangle, in this small square. So by the FKG inequality, all these events are increasing, so it's going to be larger or equal to 1/8 for the first event, 1/8 for the second, and 1/2 for the last one. And this is the end of the proof. So this is, I think, the shortest way to prove this theorem. Notice that it's based on many, many things. I mean, you use self-duality, right? You use symmetry, in many places. And when I say symmetry, there is this symmetry, and there is even another one. And there is a rotational symmetry. You use quite a lot of symmetries in your model. Getting rid of this assumption is actually quite hard. Self-duality, it's not that difficult, but definitely the symmetry assumption is a very, very tough thing. And physically, it's very interesting to try to get rid of that. So why did I focus on this theorem? Because there are many, many applications of this theorem, and I will mention some of them in the next lectures when I will really do it for other models. So I'm not going to focus too much on them now, but let me just mention for people who know a little bit. Well, first, it gives you a proof of the absence of infinite cluster. You can try to use this thing to prove that there is no infinite cluster. It's a nice exercise, which for percolation is useless because we already have Zhang's argument, but for the other models, we won't have this, so we will need a Rousseau-Simon wedge type argument. It gives you polynomial bounds for arm exponents. For instance, the probability that 0 is connected to distance n. If you use this, you can prove that it decays polynomially, and it doesn't decay faster than polynomially. That's the kind of bounds you can get. You can get even more precise universal exponents, for instance. You can get scaling relations between the different critical exponents. You can get tightness of interfaces. I mean, you have many, many, many things that you can get from this theorem. It's basically the main tool to study the critical phase that we know of. As soon as you don't have that, you are basically, well, at square one. So I will give you examples in the context of dependent models, so I'm not going to focus on this here. OK, well, that was everything I wanted to say on Bernoulli percolation. So now we are going to change a little bit and study dependent models. So our goal is really to get a geometric representation for spin models, and in particular for Potts model. We said that we would focus on Potts models. So let's try to get a geometric representation for them. So it's 3, what we call the 14 Castellan percolation. So it's also called, and I'm going to always switch between the two because, well, bad habits. This is also called the random cluster model. I basically dislike both names, but random cluster models, there are many ways of doing random clusters, so I don't like this name. And 14 Castellan percolation, it's a good name because that's the name of people who introduced it, but it's too long to write. And too difficult for me to remember. OK, so definition. So it's going to be a little bit more difficult to define than Bernoulli percolation. So I will start first by really saying that we will need G to be finite in order to define the model. So before, for Bernoulli percolation, it was very simple to define it in infinite volume directly. Here, we need to define it in finite volume. Then we will see how we define it in infinite volume, but first in finite volume. And since we are in finite volume and we are looking at something with dependency, we will need to encode somehow how this graph is embedded in my plane. What are the connections outside my graph? So I'm going to introduce the notion of boundary condition. So psi is going to be a boundary condition. So what is a boundary condition? It's just a partition of the boundary of my graph. OK? So boundary of the graph are the points that are connected by an edge to a vertex outside the graph. And psi is just a partition of this set. So you should understand this partition as telling you how the sites are connected outside my graph. So I'm going to define for a configuration omega in 0, 1 to the E of g, I'm going to define omega psi is going to be the graph obtained from omega by identifying vertices in the same pi. Okay, so it gives you a quotient of the first graph. And now I'm going to be able to define the model. So O of omega will be the number of open edges. C of omega is going to be the number of closed edges. This is just convenient notations. And K of omega is going to be the number of clusters of my graph. So now a definition. So let G subgraph of ZD, P in 0, 1, Q larger than 0. So P, you should think it as a cluster, as an edge weight, and Q as a cluster weight, and psi some boundary condition. Then we define the measure of the random cluster model with parameter P, Q, G, and psi. The probability of a configuration omega is going to be P to the number of open edges, 1 minus P to the number of closed edges. Note that if I stop here, what do I get? This is just Bernoulli percolation with parameter P. But I'm adding Q to the number of clusters in omega, and here I want really omega psi. So I count the clusters in the graph omega psi, not in omega. Okay? So depending on the boundary conditions, this quantity can differ. And if I stop like that, it's not a probability measure, so I'm going to just renormalize by a partition function. So this is the definition of the random cluster measure. And by as I said before, remark, if Q equal 1, then it's just Bernoulli percolation. So I really apologize for people who already saw these things, but I think it's important to go slowly there. So maybe I should give you a few examples of boundary conditions that you have a little bit an idea of what we are talking about. Sorry. Yeah. So the first and simplest boundary condition you can think of is just to take the partition to be just union of singletons. So you put no wirings between sides. Okay, it's like your graph is just in the middle of nowhere. So examples. So psi free boundary condition, which is going to be psi equal only singletons. So no wirings, if you prefer. And this I will denote it by psi equals 0. So if you see phi 0, blah, blah, it means free boundary conditions. No wiring between them. Then you have the wired boundary condition. And then psi is what? Is just everybody. So that boils down to say that everybody is wired together. So you see when you count the clusters in the two measure, in one case you just count the clusters of omega. In the other case, you count the clusters of omega, except that every cluster touching the boundary just count as 1. Okay? So all these clusters count as 1. So a priori, you get a very different measure. And then in this context, we will say that psi is equal to 1. Then there are two other boundary conditions I want to mention quickly. There's a Dobrushing boundary conditions. Just, I will come back to this later, but imagine you have a graph which is basically a simply connected domain. Well, I mean, at discrete level, you need to say what it means, but say it means that the complement is connected. Then, and you put 2 points on the boundary. Then you have naturally 2 arcs on this domain, which are well defined when you go counterclockwise. And the Dobryshin boundary conditions are going to be, you put wired on one arc and free on the other one. So you basically wired all the edges there. So what is going to happen with this thing is that when we are going to pass next week to what we call the loop representation of the model, this is going to correspond to what a physicist would call a domain wall boundary condition, because that's going to be a boundary condition that is going to force an interface between A and B. So that's why it's such an important boundary condition. So in this case, psi is the arc AB union singletons for the other guys. And the last thing I want to say is that imagine I give psi a boundary condition, I mean, just a configuration in the complement of G. So I have my graph G, and I have configurations like that outside my graph. There is a natural boundary condition that you can associate to that, right? What you can say is that X and Y are wired if X is connected to Y in psi. Yes? This gives you a partition of the points on the boundary. Well, I will identify the boundary condition with the configuration itself. So I will just denote, in this case, I will just denote the boundary condition like that. So for a configuration, sometimes I will write it at the top, means the boundary condition associated to this configuration. So now you can maybe understand why I put 0 and 1 here. What is the boundary condition? I mean, how could I put free boundary conditions by looking at the configuration outside my graph? Well, I can just assume that all the vertices, all the edges, sorry, outside my graph are closed, right? This will exactly tell me, OK, I am with free boundary conditions. So if psi of E is equal to 0 for every E not in my graph, I get this thing. If, on the other hand, if all the edges are open and my graph is not too, I mean, if there is only one arc on the boundary, so if, for instance, I'm simply connected, then I will recover exactly these boundary conditions. Everybody is wired together. That's why I put 1 here. So that's examples of boundary conditions. OK. Now, what is the connection with the Potts model? Because that's what we are here for. So this is a coupling which is sometimes called the Edwards-Sokal coupling for a very mysterious reason. Because basically, it actually appears directly in the Fortuyn-Castellan original paper. So I'm just going to call it coupling. So coupling with the Potts model. And then we will do a, maybe we do, well, let me just state the coupling, and we will do the proof after the break. So imagine you have a configuration. I give you omega, a configuration, a percolation configuration on a graph. How can you recover in a natural way a configuration on the Potts model? So remember, the Potts model is a spin model, so I have spins on every vertex of my graph. And this spin is one of the vertices of a polyhedron with Q states. So if you were not there last week, just think there are Q colors, and you give one of the Q colors to every vertex of your graph. So if I have a percolation model, a percolation configuration, sorry, I can naturally associate a spin configuration as follows. Take a cluster of your configuration. So let's take C, a cluster of omega, and just choose, independently at random, a spin C of C of sigma of C in the spin space, so one of the Q colors. And now, just say, OK, for every x in C, define sigma x to be this sigma C. So basically, you choose for every cluster a color, and you color every vertex of this cluster with this color. So you get a coloring. So you get a coloring of the vertices of your graph. And the theorem is the following, is that if omega is sampled according to phi 0, p, q, and g, so if I start with three boundary conditions, then, in fact, sigma is sampled according to the random cluster, Potts model with three boundary conditions at parameter beta and g, where beta is, that I don't make a mistake because I usually don't write it exactly like that, so minus q minus 1 over q log of 1 minus p. So what did I just claim? I claim that if I look at random cluster model with q being an integer, okay, it will only work for q integer here. If I look at parameter p, I recover, when I do this coupling, so I do this random coloring, I recover a Potts model at a certain inverse temperature beta, and the connection is that beta is equal to minus q minus 1 over q log of 1 minus p. Okay, so beta is a function of p. So maybe some of you already saw this thing with minus 1/2 here. And this is when you use really q colors. But the way I wrote this with tq here, I mean, the normalization changes a little bit, and you get q minus 1 over q. But, I mean, no worries there. OK, well, it's 11 o'clock. Let's do a 5 minutes break, and after the break, we prove this thing. OK?